3.4, multiplication of whole numbers. Let's finish this one up. So we were working last time on exponents is where we left off. And we had done a couple of examples with exponents over here. And we were about to start the standard or the algorithms for multiplication. I think we had done a couple of those even, right? Yep, we had. Okay. So we did the standard algorithm over on the right. We did the expanded algorithm here on the left. And then we did partial products, which I told you was my favorite. One of the things that we had left off on was that I very quickly did the standard algorithm before we left. And I told you that the mysterious things that are going on do make sense, but they feel a little bit mystical. Like there's not a lot of explanation, traditionally speaking, in why they're there. For example, one of those components is this 0 that shows up. The reason the 0 is showing up is because I'm not really multiplying by 3, I'm multiplying by 30. And when you multiply by 30, you have an extra 0, so that's what's really going on there. And then we have these additional numbers that we're adding into the next column where we're adding in the middle of multiplying as well. And that's happening as we're doing that because we're adding a 10 that we have carried over. And so that's what's happening in there too. And so there's ways that you can regroup and explain this if you're using like a concrete model like with the blocks and stuff too. So you can do that. It just requires work that's often not done when we're trying to get kids to learn how to do it, right? Let's just learn how to do it. This number crunching kind of attitude going on. And some of the others are actually a little bit easier to justify, I think, than the standard algorithm is in doing that. Okay, so let me actually show you the one that was my favorite for one of my kids. So this is called a lattice algorithm. There's some nice things about it. It looks a little confusing when we write it all down, but one of the nice things about it is that it isolates the multiplication separate from the addition and subtraction that the standard algorithm does, right? Standard algorithm merges the addition and subtraction inside of the algorithm with the multiplication. This one isolates it. And at the beginning, anyway, you can move from left to right or right to left. And so that's kind of nice as well. So we're going to set up a grid, kind of like we set up our grid for this one over here, the partial products. If we've got a 2 by 2 set of numbers, you're going to have a 2 by 2 grid. So it's going to look like something like this going on. Okay? We're going to put the number 48 on the top, but we don't put 40 and 8. We just put a 4 and an 8. And we don't put 30 and 2. We just put 3 and 2 on the right. Okay, so that's a little bit different than the partial products where we actually put the 30 and the 40 written out. Here's where it's going to look like the lattice that we had seen with addition and subtraction. You're going to make these lattice marks dividing each of your small squares or rectangles into 2 pieces. Now with partial products, what we did on this is that the grid piece that we were in, like if we were doing this 1200, it was multiplying the 40 times the 30, right? The same thing is going to be happening over here. So the first corner box is actually the row that's got the column that's got the 4 in it, and the row that's got the 3 in it, so it's 4 times 3. And 4 times 3 is 12. So we put the top number on the left, and we put the bottom number on the right. Or the first number on the left, the second number on the right, I should say it that way. And that feels like what we did when we did addition with the addition with the lattice algorithm. Okay, we put the 2-digit number, 10's digit on the left, and then the 1's digit on the bottom right. And we keep going. So we have 8 times 3, which is 24. So the 2 goes in the top and the 4 goes in the bottom. The next box down here is the 4 and the 2. So 4 times 2 is 8. So I'm going to put an 8 down here. If you want, you can write a 0 here. If you don't want to write the 0 and just leave it off, that's fine too. It doesn't have to be there. And the last one is 8 times 2, 16. And then we're going to extend this just like we did when we did addition along the diagonals. So we extend our diagonals down like this. Right. And we add along the diagonals. And once again, this mimics like we did with addition. We are not adding the 4, the 8, the 3, the 2. All the numbers on the outside are completely irrelevant at this point. We've done what we need to do with them. We're just adding the numbers on the inside of the grid. So we start at the bottom right. This is a 6, and we just write it down here. And then I'm adding 4, 1, and 8. What's that give me? 13. So I put the 3 down here, and I do carry the 1 to the next one. Then I have 1, 2, and 2, which is 5, thank you. And then the last one in the top left corner is just the 1. And then our answer is down here. Said child in my house that really, really loved this didn't do this forever. They gravitated towards doing the standard algorithm eventually, but this helped a lot for that child to not have so many things going on at one time, because you're really isolating all the different operations you're doing in a very nice, compact way. So your answer is 1,536 with the lattice algorithm, which is exactly what we got on the previous two answers as well. Okay. As with the other two sections we've done, that is addition and then subtraction, we're next going to look at mental mathematics and then computational estimation. So mental mathematics, remember, means I'm trying to do something that it doesn't require more than how many steps? 3 steps in my head, but I'm going to show the work so that I can see what's going on in your head. All right, so this is the number, or this is front-end multiplying. So front-end multiplying means taking each digit in its place value, so the 4 is the 40's place, and multiplying it by the other value, 5. So I've got 40 times 5, and I have 6 times 5. So what is 40 times 5? No. No. What's 4 times 5? 200. Yep.
It's a Monday.
Yeah, it is a Monday. All right, so we got 200. It's okay. How about 6 times 5? We can get that one down. It's 30. And then, so that's step 1 and step 2, because I've done 2 steps of multiplication. And then add them together, and I get 230 for the step number 3. The kicker here is that obviously I can only do this if I've got a single digit and a double digit, right? If I had 2 double-digit numbers, this would be more than the appropriate number of steps, unless the double-digit number were like a 2-0, right, or a 5-0. If you had a 0 on the end, you could probably pull it off. So if I had the number like 436 times 5, that's not going to work with this method. Okay, it doesn't mean there's not another method. It just means this isn't the one for it. Not because you can't do it, but because the point is to do it with mental math, and we would have more than 3 steps. Okay. We had a strategy called compatible numbers when we did addition. Here's another one with compatible numbers for multiplication. Our goal with compatible numbers for addition was adding things together to get to be 10. That was usually our goal, 10 or 100, something that was lots of zeros on the end. It was nice numbers to add, it gets you zeros. Here, we're not adding, we're multiplying, but the goal is kind of the same. We're trying to get values that give me numbers with 0 on the end. For example, if I multiply 5 times 2, that's very nice, because 5 times 2 is 10. And you have a couple choices left of what you could do. Do you want to do 4 times 5, or do you want to do 8 times 5? 4 times 5. Okay, so either will work. What is 4 times 5? 20. Okay, so while it looks like we've got lots of steps, we're getting values that have zeros on the end. We've done 2 steps so far, and we can actually do the multiplication that follows one right after another without any carrying or borrowing, making it a single step. For example, 20 times 10 is 200 times, oh, what was left? 8, I almost said 6. 200 times 8 would be 1,600. All right, because of those zeros on the end, it makes all the multiplication possible to be done at one time, is basically what's going on. That's why we're getting away with it being kind of 2 steps in one. It's because of the zeros for our friends. Okay, the next one is the most interesting one, and it's the most unlike anything we've seen before. It's called thinking money. So we have some coins in our U.S. currency that we're going to think of in particular in correspondence to certain ones of our multiplication facts. So thinking money only works for things that are coin values. So tell me some of your coin values. 1, which is obviously not really one we care much about for this purpose. But 5. A 5 is the value of a nickel, right? So when we think of multiplying by 5, that's what we're going to do on this one. We're going to think about having nickels, okay? What's another coin we have? We've talked about pennies and nickels. Dimes.
Dimes and quarters. The other one we're going to do an example of here in a moment is a quarter with the same idea in mind. Dimes are really nice, but they're easy to work with because they've got a 1 and a 0, so we don't really use thinking money much with them, but they're going to come into play on this one. So let's see how this works. So we're going to think of this 5 as being a nickel. So this is essentially saying that we have 46 nickels. But I'd like for you to trade your nickels in for dimes. If you had 46 nickels, how many dimes would that be? Nope. How many? 23 dimes. Okay, so Mackenzie, you got the 23 dimes and you're correct. Can you explain why? Nickels are half worth of a dime. So every two nickels, we could pair them up and we could make a dime. So if I took the nickels and halved it, I'd get 23 because I'm pairing them up in groups of 2. And every group of 2 nickels will become a dime. Are you with me? Mm-hmm. Okay, think of it in a smaller number. Think about having, let's say, 8 nickels. If you had 8 nickels and you paired them up, I can even draw a picture if it's helpful. So you had 1, 2, 3, 4, 5, 6, 7, 8. So these are nickels, right? So this is my 8 nickels, and this one becomes a dime. And I would have how many dimes? 4, half as many. So when I'm changing my nickels into dimes, I get half as many. And 46 is pretty nice, actually, all around to divide by 2. So I have 23 dimes. So what is 23 dimes? Well, a dime's worth 10. What's 23 times 10? 230. Yeah, 230. I promise the answer's not always 230. We've done a couple of them now that are, but yeah. It's easier to multiply by 10 than it is by 5. I mean, it just is. Now, on this one, it's much like the front end multiplying. We did this with another method. So if you had this problem, either of those methods will work just fine. But with thinking money, I could use a 3-digit number and it would work too. And I couldn't do that when I was doing it with front end multiplying. We talked about that. But if I had, 230 nickels, right, 230, say, times 5. Well, this would be 230 nickels. And I would half it. Well, that's 115 dimes. And 115 dimes would be 115, and then I tack a 0 on the end. Does that make sense? So that's thinking money with times 5s. I think it's even maybe more helpful with the 25. This one we definitely are not doing front end multiplying. I have a 2-digit number times a 2-digit number. That's far more than 3 steps. So on this one, it's much nicer to think of this 25 as a quarter. So we have 44 quarters. What is a nicer way that we could express quarters? Easier number to turn. What could I turn my quarters into that would be more friendly? $1. So how many quarters make up $1? 4 quarters are in $1. So if I have 44 quarters, how many dollars will I have? 11. It's $11. And in very much the same way that I divided my nickels by 2 to get a dime, I can divide my quarters by 4 to get $1. And $1 represents the number 100. So what's 11 times 100? 1100. So we're using money to our advantage to turn things into things with zeros. Like, that's our goal. We like zeros. Multiplying with zeros is very nice. And so that's what we're doing for this. Obviously, 44 divided by 4 very nicely. Other numbers do divide by 4, but maybe they're not quite so obvious. So it might not be quite so simple as looking at it and just being able to say, oh, look, easy, it's 11, right, or whatever. You might have to think a little bit more for the division by 4 part of it, but it would still work if you've got a multiple of 4 there. All right, let me look with you then at one computational estimation.
This is estimation. Estimation means I'm not going to get an exact answer, right? It's a rounding, it's an approximate, it's something that gets me close enough without being extra work. I'm just going to try to be close enough. So I mentioned this is a 3-digit number times a 1-digit number. Okay, so if I actually used front-end estimation, it would take me, I'd have to do 300, whoops, let's get it black, 300 times 4. I'd have to do 80 times 4, and I'd have to do 6 times 4. That's already 3 steps. And then I'd have to add my 3 numbers together, which would make 4, right? That's what it would look like if I did front-end estimation, or front-end mental math like I did before. So what I do for front-end estimation is that I simply don't do the last one. It's inconsequential. It's not very big. It's a 3-digit number. The 6 times the 4 isn't going to substantially change my value at the end, right? So we do 300 times 4, and 300 times 4 is 1,200. Good, 1,200. We have 80 times 4. 320, yeah, it's 32, and then a 0 through 320, and then we add them together to get, yeah, 1,520 or 1,520. And the actual answer is 24 more than that, 1,544. But again, the point is we're close, right? So we use just the first 2 digits, which we can even go with a 4-digit number, a 5-digit number, right? It's just got more than 2 digits in order for it to be estimation on this. And we multiply that first number, whatever it is, first 2 digits, right? So if you had something really ugly, you have 443,000, oops, so we're putting them in here, 198, something like that. We just use the first 2. We multiply that with whatever we had going on after this. This is times 6 or whatever next, right? We just use the first 2 digits. We'd ignore the rest. Any questions on any of the mental math or computational estimation problems? All right.